Second half of section 10.5 is the probability of dependent events. When we have dependent events, that means that the outcome of one event does affect the other. So that's going to change the probability as you go. Let me show you what I mean. Let's compare. We're going to compare actually an independent with a dependent and see what it does to the probabilities first. We've got a deck of cards, a regular 52 card deck of cards. And what is the probability that I draw first a heart and second a club from that deck? Now, it's important that you answer the question, well, are you replacing that card in the deck or not? All right. So in this case, we're going to replace the card. So I want to know what is the probability of drawing a heart and a club and with replacement. So that just means that I'm going to take the probability of drawing a heart times the probability of drawing a club, just like we did in the last section. So the probability that you'll draw a heart, well, there's 13 hearts out of 52. And the probability that you draw a club, well, there's 13 clubs out of 52. So you can reduce that down and get 1 over 16. And you can divide it if you wish. 0.0625 is your probability that you will draw a heart. Put the card back in and shuffle them, and then draw a club. Now, what if you want to know what is the probability that you'll draw a heart first and then a club, but you don't put that heart back in? So in this case, the probability that you draw a heart and a club, the way you represent that is, what is the probability? You're going to take the probability that you draw a heart times the probability that you draw a club given that you've already drawn a heart. All right. Do you remember that we did this? This is the conditional probability. So this shows this is not dividing by. This says, I want to know the probability that you draw a club knowing that you already drew a heart. Okay. So this shows that conditional probability. So in this case, the probability that you will draw a heart out of a 52 card deck is still 13 out of 52. Now, if you don't put that card back in, if you place it aside and now you draw from these cards, you don't have 52 cards in your deck anymore. You still have 13 clubs available, so you have 13 clubs possible, but you only have 51 cards to draw from. So now the probability is 13 out of 51. So in that case, you simply multiply across and then divide, and you end up with 0.0637. And if you'll notice, I'm not doing a lot of this computation anymore on the videos. You can do those on your calculator real quick. Pause it if you need to and make sure that my calculation is correct. So you can see that the probability in this case is actually greater that you're going to draw if you don't replace than if you do replace. All right. Let's see. Oh, okay. So same type of thing, still working with dependent events. If we've got, okay, so I realize this is not true in Alaska, but I got this example out of the book. So we're going to move down to the lower 48 for a few minutes here. And we've got a choice of 8 different internet service providers. Wouldn't that be nice? 8 different internet service providers. You and 3 other friends are going to randomly just choose an ISP. What is the probability that you'll each choose a different ISP? All right. Well, if you want to choose differently, that means that once one has been chosen, it's no longer in the options, right? So what you're going to do is this. The probability that the first person chooses a different one is going to be 8 out of 8 to choose from, right? So then you take that one out of the running. You still have 8 that you're choosing from, but only 7 of those are actually favorable options. Okay, so you have 7 favorable options, but you still have 8 ISPs that you're choosing from. Okay, so then the next person comes in and they only have, they still have the 8 to choose from, but only 6 of those will be different from the others. And the same happens again. Remember, this is just like if you, anytime you have more than one probability, you can simply keep multiplying them over and over again. So the fourth one only has 5 favorable choices, 5 choices left that are different from the others, but you still have 8 to choose from. So now just on your calculator, take 8 times 7 times 6 times 5 and divide it by 8 to the 4th, and you should end up with roughly, well, I guess it's 105 over 256, and that's roughly 0.41. All right. Okay, so do you see the difference between, in this one, the denominator got lower because we don't have as many cards left to choose from. In this case, the bottom number stayed the same because we still have 8 choices to choose from, but now we have less that are favorable, that are what we want. Okay, so that's why the numerator went down in this one and the denominator went down in that one. Okay, last problem I have is a little bit confusing, and what they've done in the book, and I was like, oh, that helped, that made so much more sense, is actually use a picture to indicate what's going on. So let me show you how to do this, because conditional problems and dependent problems can be confusing because one affects the other, and so you've got to make sure, well, what effect does that make, and how does that determine what the next choice is? So we've got a manufacturing line at a factory. On that manufacturing line, 20% of all the items that are produced are actually defective. So they realize that there's an issue here, and so they're inspecting them. All of the items that come through the line are inspected. Now, as they go through the line, though, they've discovered that 10% of the items that go through the line, for whatever reason, maybe they're going too quick or the person isn't paying attention, but 10% are incorrectly classified. We want to know what percent of the items that go through the factory are classified as not defective. All right, so let's start out. What we're going to do is we're going to create a tree to show what our options are. So on the manufacturing line, 20% are defective. So we're going to put defective and not defective. So 20% are defective. Well, that means that 80% are not defective. Those are pretty good odds, don't you think? All right, so now when they go through the line, 10% are incorrectly classified. So these would be classified as defective. So this is the what's actually going on, and this is the classification, okay? So these are classified as defective, and these are classified as not defective. And these are classified as defective, and these are classified as not defective. Okay, so now, but we said 10% are incorrectly classified. So that means if these are actually defective, 10% are going to be classified as not defective, which means 90% are actually defective, and they're classified as defective. These 80% are not defective, 10% are incorrect. So if these are not, then 10% are classified as defective, and 90% are classified as not defective. So what we want to know is what percent are classified as not defective. So we want this part and this part. Now this is where we have the probability that they're classified not defective, given that they're defective, and this is the probability that they're classified as not, given that they are not defective. Does that make sense? So if I want to know if they're classified not defective, given that they are defective. So 20% are defective, and I'm going to take the 20% times the 10%, And that gives me this probability that the probability that they're defective and they're classified as not defective. So that is 0.02. And then the probability that they're classified as not defective, given that they are not defective, is going to be 0.8 times 0.9, or 0.72. So now we're going to have to multiply those two together. Or wait, we don't multiply them, we add them. Right? So the probability of this and the probability of that together is 0.74, or 74%. All right? So if 20% are defective, but 10% of those, and of always is your keyword, of means times. So 10% of the 20% says that 0.02 are not defective even though they say they're defective, and 90% of the 80% are not defective and they say they're not defective. So when we add those two areas together, we get 74% that are classified as not defective. That's pretty good. That's pretty good odds. We did pretty good. Okay, good luck, do well, and I'll talk to you soon.